Good morning, students. Today, in the lecture series of operating system, we will discuss process synchronization. In this process synchronization, first of all, we will discuss the basic points. We will learn about IPC, that is the inter-process communication. We will also discuss about race condition, and we will discuss a very important problem that is called the critical section problem, and we will discuss about synchronization hardware. So let's start with the inter-process communication. Processes with a system may be independent or cooperating. Um, Cooperating process may either directly share a logical address space, that is both code and data, or be allowed to share data only through files. The former case is achieved through the use of lightweight process or thread. So as we know, processes are heavyweight and threads are lightweight. So cooperating process can affect or be affected by other processes, including sharing data. Regions for cooperating processes: information sharing, computation speed up, modularity, and convenience. So cooperating processes, since they are sharing the data, so they need inter-process communication. That it means the processes will communicate with each other. So two models of inter-process communication are: number one is the shared memory. So the processes can communicate with each other, number one, with the help of the shared memory and with the help of the message passing. So these are the two ways. One is called the message passing and another is the shared memory. So here you can see the two figures. The first figure is sharing the two communication between two process A and B with the help of the message. In this figure A, you can see there is a kernel and there are different messages M0, M1, M2, M3, up to Mn. And so this is a message Q, and these two process A and process B, they are communicating with each other with the help of this message Q. Shared memory: in this shared memory, the two processes, process A and process B, can communicate with each other with the help of this shared memory. Now, actually, there are two processes. One is called the independent process. The independent process cannot affect or be affected by the execution of another process. Since the processes are executed independently, that is why the effect of one process could not make effect on other. So the problem arises when there are the cooperating process. So cooperating process can affect or be affected by the execution of another process. So advantages of process cooperation: number one, information sharing, computation speed up. So mean to say, one advantage of the process cooperation: information sharing. Since the cooperating process use the shared space, so information is shared between different processes. Computation speed up: since they are sharing the same address space, so the computation speed up. Modularity and convenience will also be there. Modularity and convenience will also be there with the help of the cooperating process. When there is one condition that is called the race condition. Let's see what is that. When more than one processes are executing the same code or accessing the same memory or any shared variable, in that condition, there is a possibility that the output or the value of the shared variable is wrong. So for that, all the processes doing race to say that my output is correct, this condition known as race condition. Several processes access and process the manipulations over the same data concurrently, then the outcome depends on the particular order in which the access takes place. One is this is very important problem that is called the critical section problem. Suppose consider a system consisting of n process P1, P1, P2, P3 or Pn or P0, P1, P2, Pn minus 1. Each process has a segment of code called a critical section in which the process may be changing common variables, updating a table, writing a file, and so on. The important feature of the system is that when one process is executing in its critical section, no other process is to be allowed to execute in its critical section. Thus, the execution of critical section by processes is mutually exclusive in time. The critical section problem is to design a protocol that the processes can use to cooperate. Each process must require permissions to enter its critical section. The section of code implementing this request is the entry section, and the critical section may be allowed by an exit section. The remaining code is the remainder section. So the critical section is a code segment that can be accessed by only one process at a time. Critical section contains shared variable which needs to be synchronized to maintain consistency of data variables. Now see, here you can see in this entry section, the process request for entry in the critical section to entry section. So there is one entry section and there is one exit section, and there are the remainder section as I have discussed earlier. So solution to the critical section problem must satisfy the following three requirements. Number one, mutual exclusion, progress, and bounded waiting. Mutual exclusion: if process Pi is executing in its critical section, then no other process can be executing in their critical section. So, is it clear? Mutual exclusion means if a process P1 is executing in its critical section, then no other process can be executing in their critical section. First. Second is progress. If no process is executing in its critical section and some processes wish to enter their critical section, then only those processes that are not executing in their remainder section can participate in the decision on which will enter its critical section next. And this selection cannot be postponed indefinitely. The third is bounded waiting. There exists a bound on the number of times that other processes are allowed to enter their critical section. After a process has made a request to enter its critical section, and before that request is granted, we assume that each process is executing at a non-zero speed. However, we can make no assumption concerning the relative speed of the n processes. Okay, so this is about the critical section. Now, we will also discuss the synchronization hardware. So, many systems provide hardware support for critical section code. The critical section problem could be solved easily in a single processor environment if we could disallow interrupts to occur while a shared variable to reuse resource is being modified. As with other aspects of software, hardware features can make the programming task easier and improve system efficiency. So the critical selection problem could be solved simply in a uniprocessor environment. Okay, if we would forbid interrupts to occur while a shared variable is being modified. In this manner, we could be sure that the concurrent sequence of instruction would be allowed to execute in order without preemptions. No other instruction would be run, so no unexpected modification could be made to the shared variable. Unfortunately, this solution is not feasible in a multiprocessor environment. Disabling interrupts on a multiprocessor can be time consuming as the message is passed to all the processes. So this message passing delays entry into each critical section and system efficiency decreases. Also consider the effect on a system's clocks if the clock is kept updated by interrupts. So this message transmission lag delays entry of threads into critical sections in the system efficiency decreases. Okay, so this is you know the all about the synchronization hardware, and in the next topic, these are some references, and in the next topic we will discuss about semaphore. So here I'm stopping. Thank you for listening patiently this lecture. Okay, thank you.